In terms of analytical methods for solving ODEs, we have four broad categories listed here. First is the idea of separating the independent and dependent variables. The second is to find a method to turn the equation into an exact form where the differential equation is in some sense an exact derivative, and this often involves finding an integrating factor for the equation. A third method is the so-called method of variation of parameters, and you will see why this method is so named. And finally, there is a broad class of methods that are based on use of transformations to reduce the equation to a form which may be familiar from other methods and so on. And there is a systematic approach to this which is called Lie group analysis, and this is a more advanced technique, and I'm referring to it here so that you know about it, but we will have only occasional mention of this. Having anticipated the nature of the solution to the particular equation that we were talking about, let's turn to solving the problem in detail using analytical methods. So we're going to look at two different methods. Remember, this is the problem, differential equation and the initial condition is stated. In the first method, we will use the idea of separating the independent and dependent variables, and then we will consider a different method. So the idea of separating independent and dependent variables is very simple. We rewrite the equation in a way, so this is the equation, original equation just rewritten, and we rearrange the dependent variables all on the left hand side of the equation and the independent variable on the right hand side of the equation. So at this stage we have separated the dependent variables on the left and the independent variables on the right, and this will then allow us to solve the problem further. We begin by recognizing that the left hand side can be written as the derivative of log of modulus of y minus 3. Reason the modulus sign is put is you can expand the two cases. When the argument, when y minus 3 is positive, you can see that derivative of log of y minus 3 is simply dy over y minus 3, and when the argument is negative, then there is a minus sign, and so in order to absorb the minus sign, we have the mod over here. So left hand side is equal to what we had before, and the right hand side is simply minus dt over 2, and so now since we have derivatives, exact derivatives on both sides, we are ready to integrate. So we can integrate this equation immediately, and that gives us log of mod of y minus 3 on the left hand side equals minus t over 2 plus an arbitrary constant c1. And so now we are ready to do algebra with this. So we take exponential of both sides, and so we then have mod of y minus 3 equals exponential of this, which is equal to exponential of the constant times the exponential of this factor, exponential of minus t over 2. And so just carrying that one more step, we can say that y minus 3 equals plus or minus exponential of this constant c1 times e to the minus t over 2, and this part here we can call another constant c, which is the next step here. Y minus 3 equals some arbitrary constant times e to the minus t over 2, and now we come to apply the initial condition. We recognize that when t is equal to 0, the value of y must be y0 that was given. So y is replaced by y0. y0 minus 3 must be the value of this function when t is equal to 0. So we put 0 here, and then recognize that e to the minus 0 is 1, and so this thing is equal to c. This gives us the value of c is equal to y0 minus 3, which we can substitute back in the original equation like shown here. We are just replacing c by y0 minus 3, and then we can just rearrange it into this nice clean form that y is equals to y0 e to the minus t over 2 plus 3 times this factor. And this, writing it this way, allows us to interpret the solution in a clean way. The initial condition effect decays by this factor, and this is the solution that it becomes at large times. Remember, this will go away and the solution will become 3. So now that we have finished discussing method 1, we're going to switch to look at method 2, and that's written here on the board, and so we will talk about method 2. And method 2 uses a very important idea of writing the equation so that it is expressed in terms of an exact derivative, and this often involves finding an integrating factor for the differential equation. And so remember, this is the differential equation as given, and so we're just rearranging it. We're moving this term to the left hand side and keeping that on the right hand side as original equation. And so the idea is that the left hand side of the equation, can we express it as a derivative of some function, as an exact derivative of some function. And so in order to put it in that form, we multiply the equation, both sides of the equation, by some unknown function mu of t. And so multiplying this equation by mu of t, we have mu times dy dt, and then mu times 1/2 of y, and the right hand side is then 3/2 times mu. At this stage we don't know mu, and the idea is to find that mu which will allow the left hand side of the equation to be expressed as an exact derivative. And so if the derivative, if the left hand side is an exact derivative, then it should have a form like shown here, d dt of mu times y. And so by chain rule, if we expand it, we will have mu times dy dt plus d mu dt times y. That's what chain rule for derivative of a product of two functions is. And so comparing this left hand side with the actual left hand side that we have, we see that we need to make this identification that d mu dt, if it is equal to mu over 2, then this equation as we have it will actually be in the exact form. And that is the identification that we're going to make, and that will allow us to solve the problem. So as we saw, in order to have the equation in exact derivative form, we need to choose mu so that mu satisfies this equation, d mu dt equals mu over 2, and that has a very straightforward solution that we can integrate once, and we will see that mu equals exponential of t over 2. In general, there can be a constant of integration, and I'm choosing the constant of integration to be 1 here. So this is one possible integrating factor. And so once we have this factor, then the equation is now in exact derivative form on the left hand side. The ODE, remember, is now in the form d dt of mu times y, and the right hand side is 3/2 mu, and mu is a known function now, which is equals to 3/2 times e to the t over 2. Mu on the left hand side is also known, but the important thing is that it is now, as the exact derivative, is a derivative of this product, and so we can integrate this product immediately. And so integrating once, we have mu times y minus the value of this product when t is equal to 0, so mu of 0 minus y of 0. We are doing this integration with finite limits between 0 and t, and so the right hand side is the integral of this expression between 0 and t. So integral of exponential function with some factor is the exponential function divided by that factor, so that's why we have this 1/2, and then we need to evaluate this between 0 and t. And so when we do that in the next step, expanding this out, mu at t is an exponential function, y is just y. Mu at 0, when t is equal to 0, this exponential function evaluates to 1, so that's this 1, and y at 0 is y0, that's the initial condition given. On the right hand side, we evaluate this quantity at t, which is simply this expression, because this 1/2 creates a multiplier of 2 which cancels the denominator, and then evaluating this at 0 gives us this value minus 3, which needs to be subtracted. And so this is now our solution. We can just rearrange it in terms of y, and that we can do by pre-multiplying everything by e to the minus t over 2, so that would remove this factor, and that will give us this solution as shown there at the far end. And this solution we can compare with the solution we had obtained with the previous method, and you will see that we have obtained exactly the same solution.